Well, hello and welcome YouTube. Mr. Robinson back here with yet another brand new exciting video, all math-based of course, and as always, it is an honor and a privilege to be serving you here today, as it is every day here in my virtual classroom. Okay, step on aside and let's get an overview of some things that I've been talking about recently when it comes to graphing polynomial functions of any degree of any sort, some leading coefficients, some factored form, some standard form, even writing equations in standard form from the graph and whatever it is. Even and odd functions, where those exist, where those take place there, function operations, adding, subtracting, multiplying, even composition of functions, and how we use them in inverse functions or testing for inverses. So I have front, back, 2 pages, 4 total sides of 9 overall questions for us to take a look at. Some are in parts and things like that. You want to check the PDF down below and download and do the same thing you can here. This is not in any sort of order. When I did construct this, I wanted to make sure that they fit on printable pages. So I think each page has a problem where you do have to draw a graph of some sort. So it's going to be a little scattered. It's going to be a little less taught and a little more doing, I suppose. It all depends on the kind of problem we have here. And some of it even falls back on some of the things we did from a previous unit from a few weeks ago, if you were following the chain of uploads here. Now follow this one right in and let's take a look at what we got here. You can probably guess what color I'm going to start with. I generally tend to default with, any takers? Any takers? Blue. All right, I'm going to start with some blue right here. Let's go ahead and crack number 1. Graph a possible function for f of x below and label any relative max and min points. And by possible just means there's no scale on y here. We got to make sure that it looks, we don't really have the relative mins and maxes in play necessarily, but we're going to locate where they would be. We just don't have the actual heights of them. That's a calculus thing. All right, so this 3, I'm not going to say it's irrelevant. It's going to have to do with the y-intercept, but it's a positive number. That's all I care about. Positive. And then we have an x times x squared times x cubed, which gives us an x to the 6th. The degree is 6. Uh-oh, I hope my pen's not going to be doing that today. The degree is 6 here. That means it's an even number. And an even number means with a positive leading coefficient here, leading coefficient positive, means we are going to have a start up, finish up quality to our graph. I don't know exactly what it's going to look like just yet, but we'll go and take a look based on x-intercepts. X-intercepts are actually asked for down here, and I'm going to go ahead and write them based on what we are looking at inside here. If we set y equal to 0, then if x plus 3 equaled 0, x would equal negative 3. If x plus 1 equaled 0, x would equal negative 1. That is a multiplicity of 2. We'll talk about that in a sec. And if x minus 2 equaled 0, x would equal 2. So the 3 x-intercepts are negative 3. Oh, you can't see down here. Just 1 sec. Negative 3, negative 1 with a multiplicity of 2, and then 2 with a multiplicity of 3. So that's where we're going to be crossing this x-axis, or at least hitting it right here at negative 3, negative 1, and positive 2 right here. Now, as far as the rest of the graph goes, it's all about that start up, finish up quality here. We'll talk about end behavior as well when we get this done, but we're going to start up and go through negative 3 down below. It's going to hit negative 1 with a multiplicity of 2, which means as it turns around at some relative min, it's going to bounce off this negative 1 right here. And then it's going to go back down below somewhere, and it's going to curve back up. I know my picture's in the way, but it's going to curve back up here to 2, and it's going to be snaking through that 2 like a cubic, like that right there, and back up and through. I'm sure I could do better, but that's the appearance of it. So it goes straight through negative 3, and it snakes through that 2 there. If I move this up, you can kind of see that snake aspect of it. I'm sure I could do that better, and I probably should. But make sure you're not going just straight up through 2. It's not this. It's not this right here. That's a multiplicity of 1. This is a multiplicity of 3. Should have that bounce off effect. You know, I will do that one better because I don't know if I'm exaggerating it enough, at least for the sake of what I really want to do there. So that's going to be probably a little more like that. That was pretty good, at least compared to the bounce off. There's my multiplicity of 3 I'm looking for. Okay, start up, finish up qualities right there. Label any relative max and min points. And I know my picture's going to be in the way for a lot of these graphs here. Here's a relative min. They're also called local mins, local maxes. Here's a relative min. Here's a relative max where it tops out there. And this is neither a min nor max right there. It never changes direction. It flattens out and curves right back up. So that's neither nor. And that's it for relative mins and maxes. Turning points, wherever they do turn from increasing to decreasing or decreasing to increase rate. Decreasing to increasing right there. Is there an absolute max, absolute min, or none? When you have an even degree function such as this one right here, there is an absolute minimum. It does bottom out somewhere. So this does have an absolute min. It would actually happen to be, if I start it right here, it would actually happen to be this guy right there. That's probably the lowest. Now maybe you wouldn't know. Is this going to be smaller, lower than this, or whichever way? That's why we're not indicating right now. I'll go ahead and say that my guess is as -1 to 2 is farther apart from each other. That's 3 away from each other. This is 2 away from each other. That I'm guessing that this one's going to be lower. That's at least my thought. I'm just telling you where the absolute min is as far as it bottoms out. There is no absolute max. It goes as high as possible. It goes forever. So there's an absolute min with that. End behavior. As x approaches positive infinity, so does y. Go to positive infinity there. Right and up, and left and up right there. That's the start up, finish up thing. When I say start up, I mean coming from the left side. It's actually going down, but it starts from the top and it finishes back up. And the y-intercept's the last thing right here. Now this is where the 3 actually does matter with regard to the value itself. If x equals 0, we're talking about f of 0 here. That's 3 times 0 plus 3 times 0 plus 1 squared times 0 minus 2 cubed. I'm plugging 0 into those parts. And that's going to be 3 times 3. I'll just do this. 3 times 3 times 1 times -8, which is 9 times -8, which is -72. This thing hits -72 down here, -72 down there, and I guess that kind of agrees with our graph that at least it's negative. Obviously, it's not to scale with the x's, but the y-intercept there is -72. I'll make sure all the do the plus, -2, good. All right, so -72 right there, and that fills out our graph, what we're looking for. You can check it on a graphing calculator. It should end up being the same thing, just super tall in comparison to what I did. You'd have to shrink your window. All right, find the inverse of each function and write using inverse notation. So now this is an idea where you swap your x and y values in a variable, your variables right here, and then you end up solving for y again. So f of x is y. I'm just rewriting that right there. I'm going to go ahead and take its inverse and swap the x and the y. X equals cube root of 3y minus 2, like that. Now I'm going to go ahead and solve for y again. We got to do all the inverse operations that are affecting y. Do the last thing that affects y and kind of take care of it first. Y is being multiplied by 3. That's being subtracted by 2. That whole thing's being cube rooted. Let's go and cube both sides right there to start getting y by itself, as the cube and cube root cancel right there. We get x cubed equals 3y minus 2. And now we're going to add 2 and divide by 3. I hope this doesn't take too long here. 3y equals x cubed plus 2. And then divide by 3, you get y equals, I'll just put x cubed plus 2 all over 3. Different couple ways you can write that there. Inverse notation for that is going to look like this. Kind of looks like negative first power. So x cubed plus 2 all over 3. I think that's a good look for one. Or 1/3 x cubed plus 2/3, something like that. And there is the inverse with the inverse notation right there. We'll do the same thing right here. F of x equals 2 over x plus 1 minus 4. So y equals that guy right there. Swap the x and y. So x equals, here's our inverse portion. So, once we swap x and y, we're now in inverse territory. Inverse territory is here and here. We have now, these are 2 different graphs now. One is, if we graphed it, one reflects across that y equals x thing that we've seen. Maybe you've seen it in some of my videos before. Anyway, we got to solve for y. Y is being added with 1. It's being divided from 2. And then we subtract 4 out of that. So we're going to add that 4 first. X plus 4 equals 2 over y plus 1. And this time y is in the denominator. And we got to get it out of the denominator. I've mentioned these kinds of things before. I'll kind of write 2 steps in one here. I'm going to multiply both sides by y plus 1. By that quantity right there. And then I'm going to divide both sides by x plus 4. If I do them in both steps, the y plus 1 and x plus 4 kind of switch places right there. Boom, 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 boom. Now you have y plus 1 on the left side. 2 over x plus 4 on the right side. And then I can subtract 1 from both sides. We get y equals 2 over x plus 4 minus 1. Oh, I'm sorry. Let me put inverse notation there. So that'll be inverse of f of x. All right, there we go. So yeah, there it is. I'm trying to make sure I got all that right. It looks pretty good. All right. Determine whether f of x and g of x are inverses using a composition of functions. So instead of asking you to take its inverse and see if it matches up, we're actually going to do our f of g of x and or g of f of x. I might as well do both for the sake of this video thing, as long as things clean up well enough as far as what we want to do. I can see where maybe this one might not clean up in that same vein. Doing just one versus the other. We'll take a look. Let me evaluate that. Yeah, if I plugged this into here, then I have to work a common denominator. Maybe I won't do that. Maybe I'll just go this way instead. I'm having thoughts here. Okay. Having extreme thoughts, actually. Yeah, probably gonna do that. Okay, anyway. F of, well, I don't know, it's a video. It's a tutorial showing you what to do. If we do f of g of x, we're gonna try and see if we get x out from this, basically. So this is f of 1/2 x plus 5. G of x is 1/2 x plus 5 there. So we're gonna substitute 1/2 x plus 5 in right there. It's gonna go ahead and take its place. So this becomes 2 times 1/2 x plus 5 minus 10. Now we're going to go and simplify this thing, distribute the 2 into here, and we're going to get 2 times 1/2 is 1, so we get x plus 10 and minus 10, which equals x. So that ends up panning out to be x right there, which means that, yes, these are inverses of each other. If the composition of functions, f of g of x or g of f of x, gets you x out, exactly 1x, then you're good. If it gives you anything else at all, they're not inverses, assuming you do the math right. Let's try g of f of x and see what we get from that one. I think these should be clean enough to try both. So we'll do g of 2x minus 10, which would then be 1/2 times 2x minus 10 plus 5. 1/2 of 2x is x, 1/2 of negative 10 is negative 5, and negative 5 plus 5 is x. So once again, yep, getting there. All right, part B right here. Now, I think the cleaner one and the easier one to not deal with fractions should be, and I don't know, I'm going to think about if the other one works out in a way that I don't have to do a big expansion, but should be taking this and putting it into that x right there. So I'd rather probably look at g of f of x from off the bat. Well, I just wrote that wrong. G of f of x, which is going to be g of 8 times x plus 3 quantity cubed minus 2. And that's going to be the cube root of, and here's where we're going to put 8 times x plus 3 quantity cubed minus 2. And then it's got minus 6 on the outside here, all over 2, like that. So right here, I'm sorry, there's a plus 2 inside right there as well. So this plugged in right there. Negative 2 plus 2 actually goes away right there. And inside the cube root, minus 6 is not a part of the cube root there. But inside the cube root right here, we do now have the cube root of 8 times x plus 3 quantity cubed minus 6 all over 2. You know, I can take that cube root right here. That's a cube root of 8 times the cube root of x plus 3 cubed. Cube root of 8 is 2. Cube root of x plus 3 is x plus 3. And we get minus 6 there over 2. So again, it's the cube root of those two separate things because it's a product. You know, that's an allowed notion there. Totally cool. 2 times x plus 3, we get 2x plus 6, and then minus 6 over 2. 6 minus 6 is 0. We get 2x over 2, which is x, as those cancel out. So yes, these are inverses of each other. I'm very curious. I haven't done it yet. I'm very curious to see how the other form works putting it in. I will state you're going to have to work toward a common denominator in doing that. I want to see if it's worth its time and investment. You know, yeah, let's go ahead and do that. So I'm going to go ahead here. F of g of x. We got to do f of g of x. Because who knows? You know, maybe you're not sure which one you have. Maybe you have that as the other way. This is probably the way you would have started trying it, right? So we're going to do 8 times. Sorry, you can't see that whole thing. That's okay. I just need to see the top. Cube root. So x is now going to be replaced by cube root of x plus 2 minus 6 all over 2. Cube root of x plus 2 minus 6 all over 2. And then inside there, there's still a plus 3 quantity cubed, and then minus 2. So there's that. You know, a lot of different ways you can work this thing out. Like I said, you could do a common denominator. One other way I could do it is I could split this denominator up. I'll go ahead and do the common denominator. Times 2 over 2 right here. So that 3 then turns into, so I got cube root x plus 2 minus 6. The 3 now turns into a plus 6, and that's over the same 2. So I'm going to divide all those by that 2. Negative 6 plus 6 is 0, so those parts go away right there. And then we have 8 times the cube root of x plus 2 over 2 quantity cubed minus 2. Now, the cube root, we cube both of these. The cubed, we're cubing the cube root of x plus 2, boom, and we also cube the 2. So 2 cubed is 8. Sorry, I'm having trouble saying my cubes. X plus 2 over 8. So I cubed the top and the bottom right there. And then that's minus 2. 8 over 8 is 1. You're left with x plus 2 minus 2, which is going to give us that x right there. So once again, yeehaw. Right there, we got it. So there's a little bit of work going on, right? This is a little bit harder of an overview. We've done some of the easier ones. We're trying to review and say, do you actually know this stuff? Do you actually know this stuff? All right, next page. Find a possible function for f of x below. Label any relative mins and maxes. Same kind of thing as before for this graph. But this time, we have standard form. So it's not factored this time anymore, and I really need that factored form to get my x-intercepts. I need set x equal to 0. This is a cubic, not a quadratic. This is not equal to x minus 6 times x minus 1. No, that's x squared minus 7x plus 6. Totally different story. That is not a typo. That is a cubic. Not being a special cubic, now factoring by grouping, nothing like that. So we're going to have to use rational root theorem. We're going to have to do some of our p's over q's right here. That's right. So p's over q's, we got plus or minus 1, 2, 3, and 6. Factors of 6 over factors of 1. Factors of 6 over factors of 1. We're going to try and plug in some numbers. I'm going to start with 1 here. You get 1 cubed, which is 1, minus 7 is negative 6, plus 6 is 0. If I get 0 out, that means that 1 is one of my roots, which means I can use synthetic division on this guy and go and clean that up. Now this is 1x cubed plus 0x squared minus 7x plus 6. Do not forget that 0. It is very crucial to this problem. 1 times 1 is 1, plus 1 is 1, times 1 is 1. Negative 7 plus 1 is negative 6, times 1 is negative 6, plus 6 is 0. So ultimately, that thing factors to, this polynomial here, this is f of x equals, if 1 is your root, then x minus 1 is a factor. And then we have 1x squared plus 1x minus 6, like that. So that's a factorization. And now x squared plus x minus 6 can factor a little bit further down. We can get x plus 3 times x minus 2. So that is the factorization of this guy right here. Now, this didn't come without its merits as well, right? The degree, it shows you right now, the degree of this polynomial was going to be 3. It's an odd. And then it's a 1, x cubed, so the leading coefficient is positive. Positive leading coefficient right there. A cubic, positive, would start down and finish up and might do some stuff in between like that. So start down, finish up, boom, boom. We're going to hit these intercepts this way. We got an x-intercept of 1, of negative 3, and of 2. Those are x-intercepts. I'll label it down below as well when we get there. Negative 3, 1, and 2. So being the cubic that it is, it looks like it's going to come from the bottom, shoot through that negative 3, hit the 1, and come back up to the 2. And not the best accuracy hitting those points. Let's pretend like I did a little bit more. And that is our graph right there. At least I tried to make it our graph. So that is our graph right there. Start down, finish up. No multiplicities where we bounce off. Nothing like that. Go straight through. We're going to hit some y-intercept up here. Now that y-intercept is also revealed right here. The y-intercept is 6. 1x is 0. We get 0 minus 0 plus 6. So this y-intercept right here is 6. I think we can answer all the rest of the questions after we label. Relative max. Relative min. Sorry if you hear a garbage truck. Or recycling, I should say. No absolute max or min this time. This thing goes down forever and it goes up forever. Whole idea of absolute max or min is the absolute highest or lowest this graph goes. It goes down and up forever. So there is none. All the odd degrees will definitely have none. The even degrees should have one of them. You can't have both. Not for a polynomial. As x approaches positive infinity, so does y. We go right and up forever, finish up, and we start down, left and down right there, negative infinity. The x-intercepts we established were negative 3, 1, and 2. No. I was going to put a negative. No multiplicities. And that y-intercept there was 6. Again, it's in standard form right there. That really helps out, kind of reveal that stuff. And get used to some standard form. I think they're going to keep coming into play. So there's all that, and that's the problem. All right, next topic. Determine whether each function is odd, even, or neither. I think you can assume these go forever here. I don't know why this y is flipped upside down. I think I must have done something by accident. Must have hit a wrong button. Anyway, that's okay. It still does what I'm trying to ask it to do. Whether a function's even, odd, or neither asks what kind of symmetry it has when seeing the graph. Is it symmetrical across the y-axis right here, whereas some x would give you some y and opposite x would give you same y? Is it an odd function where some x would give you some y and opposite x would give you opposite y? This one looks like it has that. Or is it neither, where neither are true? This seems to have that symmetry across the origin right here, where when I plug in something for x, I get a y. Plug in the negative x, I get the negative y. Plug in some x, I get a y. Negative x, I get a negative y. There's not to scale with regard to the numbers and such, but I think you can hit home the idea of the odd function behavior without actually plugging anything in. This is definitely odd here. When you're given something algebraically here, our determination is plugging something in to determine it, not an actual number, because you might run into what's called a false positive. You can't prove things by example. We gotta, even if you have 100 different numbers that work, I'm sure that's convincing. But and we can use it to support, but what we're going to do is actually substitute these things here. So here's what it's saying. If I plug in x, I get this y out, whatever that is. That's the y that I get out based on plugging that x in, right? What happens when I plug in negative x? Do I get the same y? Do I get the exact opposite y? If no to either, then it's neither. If yes to same y, it's even. If to exact opposite y, it's odd. When I substitute negative x into here, negative x will literally take its place, just like we did for the f of x things, plus absolute value of negative x plus 3. Now, negative x to the fourth power is negative 1x to the fourth power, which gives you a positive x to the fourth power, the equivalent idea of it, because the negative to an even gives you a positive. Now, right here, you have to be careful with absolute values. Absolute value doesn't mean make something positive, in that this would turn into x plus 3, especially because we don't know what x is. See, whether I raise a negative number to this power or not, these will still give you the same sign regardless. Right here, if x is negative 2, it changes things. Plus, this is a quantity. This is a quantity right here. What I could do is I could factor a negative 1 out of this whole thing, and I get x minus 3. These are the tips and tricks of absolute values. I'm just showing you that right now. Tips and tricks of absolute values. An absolute value of a product is the same thing as a product of an absolute value, of two absolute values here, like that. And the absolute value of negative 1 is 1. So this becomes x to the fourth plus x minus 3. 1 times x minus 3, which is x minus 3. So that's f of negative x. So the question is this the exact same? Is this the exact opposite? Well, it's not the exact same. It's very close, but there's an x minus 3 right there. If it was the exact opposite, then you should be able to factor a negative out of all these things, and you can show that it resembles this outside of the negative that's factored. Seems to be a neither case here, a neither burger. This x to the fourth is the same. The only thing that changed was the minus 3. If you graphed both of these, you would kind of see a different result in both. This is a neither case right here. Not neighbor. It's a neither case. There we go. And the last one here, also going to substitute negative x. We get f of negative x here. And I guess there are different ways we could do it. This looks factorable even. Negative x to the fifth minus 2 times negative x cubed plus negative x all over negative x quantity squared minus 1. So that will give us negative x to the fifth plus 2x cubed, because negative x cubed is that, and then times negative 2, and then plus negative x right there, all over, that's a positive x squared minus 1, because squaring, that gives you it. And, on the top, the bottom is the exact same, so that might lend you to say even or neither, but you're actually negating something else that's occurring here, which is the negative on top. All these signs changed, which means you could technically factor out a negative right there, and you'd have x to the fifth minus 2x cubed minus x all over x squared minus 1, almost as if this negative didn't need to be just on the outside of the numerator. It applies to the whole fraction, right? A fraction is a single number, really. It's 1 divided by another, but a negative divided by positive is still a negative. So it's a negative fraction. What am I pointing at right here? What I'm showing you is that right here we have a positive version of x to the fifth minus 2x cubed plus x over x squared minus 1. On the bottom we have negative x to the fifth minus 2x cubed. That should be a minus. Plus x minus over x squared minus 1 right there. It's the exact opposite of what we had the first time. This is also odd. This is also an odd function right here. So one other way I can look at it, I don't know if changing the bottom won't help, but another way to look at the top here is if I factor an x out of there, I get x to the fourth minus 2x squared plus 1, which factors to x squared minus 1 quantity squared. Oh, this does help. X squared minus 1 quantity squared. I didn't think about this. Over x squared minus 1. You can divide one of these with one of those. That's more of a rational function thing. So now this turns into x times x squared minus 1. Whether you want to distribute or not is up to you. But when I do f of negative x now, that's f of x. Boom, boom. When I do f of negative x, that's negative x times negative x quantity squared, which is x squared minus 1. It looks to be the exact opposite of that. Here's x times x squared minus 1, negative x times x squared minus 1. They are indeed exact opposites. That's an odd. All right, I'm going to go ahead and move forward with this right here. As we're 25 minutes in, I think it's time to just advance. 4 more overall problems. Graph a possible function. Once again, label any relative mins and maxes. We are once again in standard form right here, and I have a GCF of negative x. Negative x I can factor out to get x cubed plus x squared minus 4x minus 4. This really looks like factoring by grouping, and I do believe it is. So we can factor by grouping here. Do not lose the x on the outside, or the negative x I should say. And inside, if you factor an x squared out, you get x plus 1. And you factor a negative 4 here, you get x plus 1. And with that negative x on the outside still, as this keeps factoring, that's x squared minus 4 times x plus 1. Yada, yada, keep going. And that factors into negative x times difference of two squares, x minus 2, x plus 2, x plus 1. So there's the factored form. Given that we found some other stuff right here, we have a degree of 4, that makes it even, and a leading coefficient that's negative, which even negative means start down, finish down like that. It's going to have that kind of property to it. The y-intercept, by the way, if you plug in 0 into these, it's not 4, right? It's 0. Plug 0 into these and you get 0 back out. So that's something else because it's going to hit an x-intercept of 0. Here are your x-intercepts. 0, 2, negative 2, and negative 1. Right there. That negative has nothing to do with anything regarding the intercepts. It has to do with the direction that it starts and finishes. If you flip it over, if you change it positive, the intercepts are still the same. So y-intercept of 0, because we have an x-intercept of 0. As you plug in 0 for x or 0 for y, you get 0 out for the other variable. Negative 2, 0, negative 2, negative 1, 0, and I think 2. I think that was our difference of 2 squares there. Yep. So we're going to start from the bottom. No multiplicities. We'll start from the bottom. We're going to be crossing through all these like a mouse. Up, down, up. Probably even higher. I'm running out of room there. Up and down. That's fine. As long as we keep it function like. And there is our graph with a relative max here. Relative min here. And a relative max here. Given that it's an even function, it does top out somewhere. It looks like this relative max is also an absolute max. And that's exactly what this is. It's an absolute max right there, or at least one exists. Is there anything else I have to do from the top? I don't think so. As x approaches positive infinity, y approaches negative infinity. And same is true for negative infinity right there. It seems to be going down both directions there. X-intercepts, I believe I said, were negative 2, 0, negative 2, negative 1, 0, and 2. No multiplicities to speak of. The y-intercept is 0. If the x-intercept is 0, so is the y-intercept. You can only have one of them. If crosses at 0, 0, then that must be it. So there you go. That's it for the problem. All right, perform the following function operations given f of x equals x plus 4 and g of x equals 2x squared minus x plus 5. Let's do 2 times, it says 2f of x plus 3g of x. That means 2 times f of x. That's going to be 2 times f of x plus 3 times g of x. We just simplify. There's nothing to solve. Distribute 2x plus 8. Distribute here 6x squared minus 3x plus 15. And that's going to give us, in standard form, by the way, 6x squared, 2x minus 3x is negative x. And then 8 plus 15, 23. I think I covered all the terms there. Looks like it. And that is the addition of those two with the 2 times that and 3 times that. Now this f minus g of 3x, what that means is f of 3x minus g of 3x, which means 3x will be substituting for x in all these things right here. F of 3x, I'll keep it black, I don't do this enough. F of 3x is 3x plus 4. as a quantity, well, there's the substitution, but as a quantity, I would even write it like that, just a big boy substitution, minus g of x. Now, one big careful thing is you should quantify this guy. 2 times 3x squared minus 3x plus 5. Maybe overuse of parentheses with the 3x substitution right there and right there. But the rest is really important. Oh, and even this one. But the rest is really important there. This still turns into 3x plus 4. Now, we are going to be distributing that negative. Let me first clean this up. 3x quantity squared is 9x squared times 2 is 18x squared. And then minus 3x plus 5. So now we distribute that negative and we get 3x plus 4 minus 18x squared plus 3x minus 5. My standard form will look like negative 18x squared plus 6x minus 1. If all went as hoped, it should be just that. And in black. All right, f of x times g of x, straight up polynomial multiplication right here. I was going to say 3x plus 4. X plus 4 times 2x squared minus x plus 5. Straight up distribution right here. No other qualms. We get 2x cubed minus x squared plus 5x plus 8x squared. The 4 is multiplying. 8x squared minus 4x plus 20. Combined like terms get in standard form there. We're going to get 2x cubed, I think, plus 7x squared plus x plus 20. This is actually the fastest of the problems right there. Probably the most common that you've seen. Last one says g of f of x. Now, we just did a bunch of these kinds of things when we were talking about function inverses. So let's do it right here. Specifically, g of f of x, not f of g of x. It's not your choice. That's going to, so, and that's what that says. That says g of f of x, which means g of, oh my goodness, g of x plus 4, which means 2 times x plus 4 quantity squared minus x plus 4, here's where parentheses are important, plus 5. Now, when you do 2 times x plus 4 quantity squared, you got to first do the x plus 4 quantity squared. Multiply that. That's not x squared plus 16. It's x squared plus 8x plus 16. You can distribute this negative right here, negative x minus 4, and then there's a plus 5. And yes, that is in parentheses right there for the x plus 4. So it becomes 2x squared plus 16x plus 32 minus x minus 4 plus 5, which then becomes 2x squared plus 15x. Oh, and the minus 4. I should have done that first. 32 minus 4 is 28. Plus 5 is 33. Plus 33. We're not trying to see if these can factor. I'm curious if these randomly can. This actually got really close. I think if this was a 14, it would have been actually factorable. But alas, it wasn't what we were aiming for. I could have tried to come up with a problem that can do that. All right, so those are the composite or function operations right there. Last page right here, one more graph, and then something on the bottom. I think we have to write an equation based on a graph on the bottom one. I think I recall. 4x to the fourth minus 37x squared plus 81. This is once again, this is factorable in this case. We don't have to use rational root theorem necessarily, or I assume and hope it's factorable. I came up with the problem. I didn't do it yet. I just came up with it mentally. It's going to be some sort of 4x times x scenario here. It can't be 2x. By the way, no GCF. It can't be a 2x times 2x because 37 is an even number here. Given the minus sum and plus product here, I'm really thinking the 9 and 9. And I think that was the decision here. There is a mistake on the problem then. I do have to change it. This is why I should do problems beforehand. We're going to turn this minus 37 into a, I hate doing this, into a minus 45 right there. This was the intent of the problem. Obviously in my head I was doing some sort of negative 36 minus 1. It's negative 36 minus 9. So we are changing that right there, and that is, that's the, 4x squared and x squared. So that's the factorization of that portion right there. If we keep breaking that thing down, these are differences of two squares. 2x minus 3 times 2x plus 3. And then here we have x minus 3 times x plus 3. So again, the intent was 45. The intent was to factor in this way, I do believe. I know. That's why I should do problems before that. So that should be a 45 there. My bad. Carry on. You tried it before. You got stumped. You used rational root theorem. I'm so sorry. That was not what I was going for. All right. So right here, this is a factorization, which means we can get some x-intercepts out of this. We have x-intercepts of, if we add 3 divided by 2, we actually get 3 halves. Subtract 3 divided by 2, you get negative 3 halves. Add 3, you get 3. Subtract 3, you get negative 3. 3 halves, it's 1.5. 1.5, negative 1.5. We also know about this thing, the degree is 4. It's even. The leading coefficient here is positive. So it's going to start up, finish up. Boom. Do something like that. Have that appearance. So let's cross through these points. Negative 3 is actually the furthest left here. We have negative 3. And then negative 3 halves. That's negative 1.5. That's fine right there. We can point that. Excuse me. Positive 3 halves and then positive 3. So this must have that symmetry going on. So like right in the middle, it's going to top out somewhere at some relative max probably. It's going to top out at 81. Right? So this gets apparently tall. I mean, we can't really draw the effect of that, but it apparently gets pretty tall there. I'm just going to go and curve it on over. It's not as symmetrical as I can make it, not even close. But I'm very limited in what I'm able to kind of do here. I'll accept it. No, I won't. Make it a little bit better. Just a little bit. Itty bitty improvement. Actually looks much better. Okay, so there's our continuous function right there. Relative mins and maxes right here. Relative min. Relative min. And if this thing is truly symmetrical, then these relative mins have the same height, which means when we refer to the absolute min, which this has, both of these share the absolute min. See, the absolute min is... Actually, I take it back. I was going to say it's not about where it is, it's about the value. That's not necessarily true. Relative max is right there. So there, those, it does have an absolute min. It probably has 2 of them. But they're the same value, just at different spots. It starts up, finishes up right here. So positive infinity for both of those. Our x-intercepts were negative 3, negative 3 halves, positive 3 halves, and 3. And the y-intercept looks like it was 81. So this one right here, where it crossed, boom, 81. That was the y-intercept right there when x equals 0. So sorry again about the 45, but 45 times 0 is still 0 plus 81. That's it for that problem. I'm just moving on forward. Last problem right here. Write a polynomial equation in standard form. It's supposed to be of least degree with integral coefficients for the function graph below here. Now this thing is assumed to go down forever, all that kind of stuff. What we're going to do is pick apart backwards what we were doing before. Let's get the factored form version by finding out these intercepts and their multiplicities. So we have x equals negative 1 as an x-intercept, x equals 0, and with that bounce off, it looks like it has a multiplicity of 2. And then x equals 2, which looks like it has a multiplicity of 3, given that snakeage. It does go negative. We'll talk about that at the end, we'll talk about in factored form right here. The factored form version of this, it has an x squared right here. X equals 0 means x is a factor. Multiplicity of 2 means it's squared. Add 1 to here, you get x plus 1. And then subtract 2, you get x minus 2. With a multiplicity of 3, that means this thing's cubed. So there's a portion of it. This thing goes down below as well. That negative means that this will be, down below means it's negative as well. You could apply your own coefficient, but I'm going to keep it like that. And that is factored form. That's not standard form. What else was I going to say? I was going to say one more thing. Y-intercept. What else was I going to mention? I don't know. I probably was going to talk about the y-intercept, but I don't think. Oh, I was going to talk about the degree of the polynomial. This degree right here, it's an x squared times x cubed. It looks like x to the 6th power. So even degree, starts down, finishes down. At least makes sense to me. Okay, so let's go and start distributing this stuff out. Now, in order to do this, we can do one thing at a time here. Maybe I'll leave the negative x squared for the end. I know that I could distribute things in, but if I can keep it smaller, maybe I will, and then I'll change the signs and the degrees right at the end. You can do it however you'd like. I'm going to start with x minus 2 quantity cubed. It is not x cubed minus 8, right? You don't just cube the first and last term. There's a whole expansion to this thing. It's going to be it's going to be 1x cubed minus, or plus, I'll say plus, 3 times x squared times negative 2 to the first plus 3 times x to the first times negative 2 squared plus negative 2 cubed. That's the polynomial expansion right there. So that'll become x cubed minus 6x squared plus 12x minus 8, like that. Now we'll do x plus 1 multiplying into those things right there. Negative x squared times, this is why I wanted to keep them smaller, x to the 4th minus 6x cubed plus 12x squared minus 8x. plus x cubed minus 6x squared plus 12x minus 8. And then I'll combine like terms inside. That's x to the fourth. This is the last problem. Minus 5x cubed plus 6x squared plus 4x minus 8. Multiply by negative x squared, we will get negative x to the sixth plus 5x to the fifth minus 6x to the fourth minus 4x cubed plus 8x squared. And I'm living by that. So y-intercept is 0 seems to make sense. Negative sextic, 6 degree right there. It's downward. That seems to make sense right there. Expanded. This was the factored form right there. And standard form right there. Steal your face. All right, so that is it right here. Hopefully that overview was kind of nice and tight. You kind of covered everything under the sun there. I think I'll covered as much as I could. That'll do it for this one, guys. This is Mr. Robinson. Thank you so much for watching. And I will see you in the next one.